Okay, here we go with a lesson that I know a lot of you are not going to like. That doesn't mean don't pay attention. That means pay attention more because you're gonna have to do it. We actually do a lot of this stuff with fractions in geometry right now as well. So it's not going away. So here we go. Little review to start. Square root of 52. How do we figure that out? You should know this by now. 2 and 26. 2 and 13. 13's prime, 2's prime. Pair of 2's, that's 2 radical 13. Okay, p to the 7th, n to the 10th, I split those up. P to the 7th, it's odd, so I'm going to go with the even number right below it. So 6, and half of that is 3 with a leftover p. And then n to the 10th is even, half of 10 is 5, so that's n to the 5th. So p to the 3rd, n to the 5th, radical p. All right. So that's just a little review of stuff we've done so far, lessons 1 and 2. Lesson 3, fractions are division. And there is a division property of radicals. It's very similar to the property that I showed you in lesson 1. If I have a fraction, square root of a over b, I can split that into 2 separate radicals, square root of a over square root of b. Okay, and the reverse is also true. So how does that help? Well, look at these first two. These are both pretty easy ones. The square root of 9 over 25, I can split that into the square root of 9 over the square root of 25. Well, that simplifies even further. What's the square root of 9? It's 3. What's the square root of 25? It's 5. That one was a nice number, 3/5. Second one, maybe not quite as nice, but still pretty nice. X to the 5th and the square root of 16. Well, the square root of 16 is 4, right? Now, the square root of x to the 5th, I got to do a little work. So I'm going to put 4 here. X to the 5th, not a lot of work, but a little bit of work. It's odd. The even number right below it is 4. Half of 4 is 2 with a leftover x. That goes on top. So x squared radical x. And I'm done with that. You might be thinking, well, that's not too hard. You're right. Those weren't hard. But there is a rule with radicals. You can never have a radical in the denominator of a fraction. Notice that's in all caps and bold. It's huge. You cannot have a radical in the denominator. Honestly, I'm not sure why. You just can't, okay? In the 2 examples above, did we satisfy that rule? Yeah, we did. Look at the final answer. There's no radical in the denominator. Why did we satisfy the rule? There were perfect squares in the denominator already. Perfect squares being numbers that don't have a leftover radical. 25, the square root of 25 is exactly 5, no leftovers. Square root of 16 is 4, no leftovers. Okay, great. What happens if that doesn't happen? Square root of 75 over 12. Square root of 12 is not a good number, right? It's going to have a leftover radical, and that's in the denominator, so it's not going to work, right? Is the number in the denominator a perfect square? Just told you it is not. What do we do then? The number inside the radical is still a fraction, and sometimes fractions can be reduced. There's your clue. And you guessed it, we can reduce this fraction. I can divide 3 out of the top and the bottom. Now, one thing a lot of people do when they do that is they take the radical away. The radical has not gone anywhere. I'm just reducing a fraction. The square root is still there. 75 divided by 3 is 25. And 12 divided by 3 is 4. If I take 75 and divide it by 12 in the calculator, I'm going to get 6.25. If I take 25 and divide it by 4, I'm going to get 6.25. These two fractions are identical value-wise, okay? I'm pointing that out because the square root, a lot of people take that square root and think, oh, I've done it, I'm done, and they write 25 over 4 as the answer. It's not the answer. All I've done is reduce that fraction inside the radical to 25 over 4. Now I need to simplify it. So now I'm going to take the square root of 25 and the square root of 4. Square root of 25 is 5. The square root of 4 is 2. There's no more radical in the denominator. We're good. Okay. A couple more examples like that. 27 is not a good number, but 15 and 27, both inside the radical, so I can actually put those together. Sometimes it makes sense to put them together. Sometimes it makes sense to split them apart. This is one of those times where putting them together can be helpful. I can reduce by 3 again. 15 divided by 3 is 5. 27 divided by 3 is 9. Oh, that's great, because what's 9? 9 is a perfect square. Now I'm going to separate them again. The square root of 9 is 3. Square root of 5 is prime already, so it's just the square root of 5 over 3. You might be thinking, well, I still have a radical. You're right. It's okay to have a radical in the numerator. You just can't have it in the denominator, and we've satisfied that rule. The thing in the denominator is a 3 with no radical. Okay, number 2. There's a lot in the denominator here, but I can reduce this. Hopefully you can see you can reduce not only the numbers, but you can also reduce the x's. 118, I can take 2 out of both of those. So that would be 50 on top, 9 on the bottom. Right away, you should be saying, oh, 9, I like that because that's a perfect square. Where are there more x's? On the bottom, right? How many more? 6. Now, did that help me? Let's see. Square root of 50 on top, square root of 9, and the square root of x squared, x to the 6th on the bottom. As long as the numerator or the denominator gets simplified, we're in good shape. The square root of 9 is 3, and the square root of x to the 6th is actually x to the 3rd. No radicals left over because the exponent was even. You remember that from last lesson. Now I just got to simplify the top, which is less than 1. So that's 10 and 5. Again, we're going to go quick here. 5 and 2. That's a pair of 5s. That's 5 radical 2 over 3x to the 3rd. One more thing you want to check. It doesn't happen here, but you want to check it. I brought out a 5 and I brought out a 3. Sometimes those are going to reduce even more. You need to reduce them if you can. In this case, they don't reduce, so I'm done. That's my final answer. Okay. Now, still not too bad. Some of you might be thinking, yeah, I can do this. And some of you might be lost right now. But regardless, what happens if the number in the denominator is not a perfect square? Well, we saw that already, right? The last couple examples, they weren't perfect squares. And reducing the fraction still doesn't give me a perfect square. So every example we've done so far, it's either already been a perfect square or it's reduced to a perfect square. What if that doesn't happen? Right away, I have an example. Duh, you could probably have guessed that. So square root of 50 over 6. After reducing, which by the way, we reduce, it gives me 25 over 3. We still have a radical in the denominator. What do? We have to do something called rationalize the denominator. Okay. Yes, I know the numerator becomes 5. So that actually is pretty easy, but we need the radical out of the denominator. So keep going down here. So square root of 25 becomes 5 over, and we still have square root of 3 on the bottom. What do we got to do? All right, so this is the rationalizing step. What we're going to do is we're going to multiply the bottom by radical 3. And you might be thinking, well, why do we do that? Well, what's radical 3 times radical 3? Well, that's radical 3 squared. Now that's great. What's the square root of 3 squared? Well, the square root and the squared cancel, and I'm left with a 3. Awesome. But am I allowed to just do that? As long as you multiply the top by the same number. So what I'm doing right here, this is the rationalizing step. I got to multiply the top by the same number. Okay, so the top is 5 times radical 3 is just 5 times radical 3. I can't put those together. 5's on the outside of the radical, 3's on the inside. So this becomes 5 radical 3 over 3. Okay, I have a funny name for that little boxed part right there. We multiply the top and the bottom of the fraction by a fancy 1. I call it fancy 1 because the square root of 3 divided by the square root of 3 is just a 1. And it's a fancy one because it's got radicals and different things in it. So that's why I call it fancy one. But that's an important piece is when you multiply a number by 1, you are not changing its value. We are only changing how the fraction looks. We are not changing its value. So if you typed this right here into a calculator, 5 divided by the square root of 3, I don't know what you get, but you're going to get the exact same decimal as you would if you typed 5 radical 3 divided by 3 in the calculator. They have the exact same value. We have just satisfied the rule that there's no radical in the denominator. Okay, that's the rationalizing step. You will have to do that. Whether you like it or not, it is a standard and you need to be able to do it. Okay. So number 1, simplify each radical expression. So nothing can be reduced here. 3 is not a perfect square. I'm just going to separate them into 7 and 3. I'm going to multiply by fancy 1. My fancy 1 in this case is radical 3 over radical 3. Same as the last one, actually. This time I can do 7 times 3 because they're both underneath the radical. And I get square root of 21. Square root of 3 times the square root of 3 is the square root of 3 squared. And that cancels to just 3. Now I will see a lot of people simplify that and say, try to simplify that and say square root of 7. Don't. The square root of 21 is inside the radical. 3 is outside the radical. You cannot combine them. The answer here is the square root of 21 over 3. And I guess what I should I know this doesn't simplify, but just so you know, 7 and 3, there's no pairs, so it doesn't simplify. So it's that. Okay. Number 2, 10 and radical 6. Nothing can reduce here. You might be saying, yeah, you can. 10 and 6 reduce. You actually can't. And I'm actually going to skip down here to this step. In number 2, why can we not reduce 10 and 6? 10 is outside the radical, while 6 is inside the radical. These can never be combined. All right. So I got to multiply by fancy 1 right away, and the fancy 1 in this case is square root of 6 over square root of 6. Top is just 10 square root of 6, and the bottom is just 6. Now what happens, you see what happens here? I kind of warned you on the second one on the top here, on the top of the back page. 10 and 6 are both outside the radical. I now can reduce them. So I can take 2 out of 10 and 6. That's going to be 5 radical 6 divided by 3. Okay. 2 more. A to the 4th over A to the 9th. So yeah, we're still doing variables with this. Again, I can reduce this though. Where are there more A's? On the bottom, A to the 5th. That leaves a 1 on the top, right? There's 5 more A's on the bottom. Well, square root of 1 is just 1, and the square root of A to the 5th, I can actually simplify that. There's a couple ways you could do this. You could simplify that first, or you could just multiply by square root of A to the 5th. I'm going to simplify it first, just to show you that you can. So the square root of A to the 5th is odd. So I'm going to have the even number right before it. So 4, half of that is 2, the leftover A. So this is actually 1 over A squared radical A. Still have a radical in the denominator though. So I'm going to multiply by fancy 1, which in this case is square root of A over square root of A. I'm going to go down here. 1 times the square root of A is just the square root of A over this A times the square root of A times the square root of A becomes square root of A squared, which is just A. That's just A. But then I also have this A squared that I can't forget about. So A squared times A is A to the 3rd. Can't combine anything. That's my final answer. Number 4, I'm going to reduce the x's. I can't really reduce the 12 and the 5. I'm just going to reduce my x's. There's more x's on top, and there's 8 more on top. Now I still have a radical in the denominator, and I'm going to multiply top and bottom by square root of 5. The top's going to get a little complicated. 12 times 5 is 60, and then x to the 8th. So I guess not that complicated, but still a little bit. The bottom is square root of 5 times the square root of 5, which is 5 squared, which is cancels the radical, which is 5. Now I just have to break down 60, which is 2 and 30, 15 and 2, and 5 and 3. So that would be a pair of 2s. And a leftover 3 and 5, so 2 radical 15. X to the 8th, you should be good at that one by now. Half of 8 is 4. So it's going to be on top 2x to the 4th radical 15 over the bottom was just 5. Nothing that came out can be reduced, so that is my final answer. Okay, I know that's probably pretty confusing, but we're going to work on it in class. Let me know what questions you have, and you can get this done.